Hello everyone, my name is Qiu Shi. I come from Xiamen University, and our paper type is GeminiFS, a companion file system for GPUs. Okay, first let us see the background of this work. We all know that GPU applications is becoming extremely large and need more memory, such as large language model. And however, GPU HBM capacity is growing at a very slow rate. And to fit the application, we must expand the GPU memory. One way is memory-based expansion, such as pull together with multi-GPU or use host DRAM. And this way is quite expensive in a foreseeable future. Another way is use storage, extend the GPU memory access range to storage such as NVMe. And with the development of high-performance NVMe storage, such as ZSD and P series in Intel, storage-based expansion has been proved to be efficient and a cheap way. Okay, let us review the evolution of GPU storage system to see our motivation. At the very beginning, we use a bonus buffer on the host to transfer data from CPU to GPU. We first read the data from NVMe to CPU and invoke the GPU API to transfer data from CPU buffer and GPU buffer. This will increase programming complexity and additional memory copy, increase I/O latency and CPU costs. And then some work, such as GPU-FS and Dragon, provides POSIX-like file interface for GPU kernel. It makes program more easier. However, they still rely on daemon process on CPU to pull in the I/O request from GPU process and submit them to host the file system and to get the data from NVMe, and then still need memory copy to transfer data. The additional control plane prolong the I/O path, and the memory copy still exists. Another popular solution called GPU Direct Storage, GDS. It leverages peer-to-peer memory copy to skip the bonus buffer and decrease CPU cost when perform I/O. However, they need a non-POSIX interface called cool-file lib and it makes hard to programming. And it needs a modified NVMe driver. And this way it still rely on CPU orchestrated I/O. The above all are CPU-centric GPU solutions. They finally rely on CPU to orchestrate the GPU I/O, and they face common questions. The first one is complex storage software greatly increase I/O latency. And the second one is when performing high concurrent GPU I/O, it's bounded by the limited CPU core. We evaluate this problem by test the GPU-FS and GDS. The left picture shows the tail latency GPU-FS. Its tail latency increase dramatically when the GPU series increase and beyond the CPU core. The right side shows the GDS latency is decreased when the base size gets larger. However, the software overhead still take account about 90%. To solve the problem of CPU-centric solutions, some SOTA solution like BAM provides the GPU-centric solution. They create NVMe raccoons on the GPU HBM and register them using a process level NVMe driver. They use NVMe device like SPDK, control plane and data plane totally managed by GPU process. It makes programming extremely simple, but it still face some problems when use use SPDK. The first one is SPDK-like usage, exclusive access to NVMe device, preventing device sharing between CPU and GPU, as well as among GPU process. And the second one, due to lack of file system management, make it difficult to process the data. And the third one is when accessing data management managed by the host file system, memory copying is still required. What is an ideal AI-oriented solution? Combine the CPU and GPU solution. We think the ideal GPU storage software should have the following features. First, it must be based on a GPU-centric architecture and totally avoid CPU. And it also provides file system management capabilities. And the third one is it offers a unified namespace to both CPU and GPU. And these features makes us have to build a file system on GPU. However, the fundamental problem is that GPUs are not suitable for building a file system. A file system typically need to have the following core capabilities. First, it needs providing directories and file abstraction, and maintain related metadata such as inode. The second one is it should provide disk space management and implementing efficient address mapping, such as eccentric in x84. This requires software with complex logic and branch jumps, but GPUs are not good at it. GPUs are primarily designed to conclude and simple mass calculation. Thus, we propose a new type of file system for GPU called companion file system. We call it GeminiFS. We separate the responsibility of CPU and GPU in file system design. It's based on these ideas. The first is GPU use hybrid programming pattern, such as NVIDIA use C++ and CUDA. Thus, file access by the GPU can be managed by the CPU, such as creation, modification, and delete. And thus, we can implement a lightweight file system on the GPU that coexist with host file system, and which and file system metadata can be management on the CPU and shared with GPU, allowing GPU to submit file I/O requests directly. However, this design still faces such challenges. The first is metadata sync. The metadata had to be synchronized efficiently due to the hardware isolation. The host and the GPU actually total two different systems, and they need communications. And the second is file operations always be closely intertwined with metadata operation. And the second challenge is elimination of the NVMe device driver. NVMe now cannot be shared among the multi-device. And the third is inefficient of GPU page cache. It's come two aspects. First, page cache can only constructed within the GPU process. And second, higher parallelism of GPU lead to a higher contention when acquire pages. Finally, GPU programming complexity. This solution needs a complex memory and environment setting on CPU and GPU, make it hard to program. And here is the GeminiFS overview. It contains 4 key designs. The first is metadata embedding. Second is SNVMe, it's short for shared NVMe. The third is GPU-specific page cache, and the last one called libgemini. First of all, we realize efficient metadata sharing by embedding metadata in the file. It's just like the specific file format used in virtualized information, virtualization, such as QCore2 or VMDK. In our scenarios, CPU and GPU using the file format called GVDK. The difference is that the embedded metadata contains the physical NVMe offset. Thus, GPU can obtain file metadata and address mapping by passing the file. This strategy based on our observation on AI applications. The first, short-term data need no persistence, such as activation generated in training. Second one is long-term data is append only, such as checkpoint and KV cache. They are generated and append only and never change again. And the last one is most storage access has predictable patterns. The file size is usually determined by the model size. So we can allocate the file and its metadata. This avoids the metadata sync during the GPU processing running. And we only embed private metadata specific to each file, such as file type, file size, and index structure. And the other complex structure like directories still managed by CPU to lower the complexity. And we use simple 2-level mapping table, otherwise tree structure such as extend tree, to lower the complexity of address translation. And then we provide a CPU and GPU share NVMe driver to share NVMe between CPU and GPUs. The key insight is that the GPU only needs the NVMe IO queue, not the admin queue. We modify the NVMe driver to map IO queue and store to GPU memory during the initializing phase and reuse GPU NVMe driver provided BAM so that the GPU and the CPU can construct the control plan concurrently. And third, we provide a GPU-specific page cache design. We first enable page cache sharing during GPU process to minimize memory cost when multi-same GPU process open the same file. Second, we also lower the load contention. First, we acquire page at the warp level rather than the serial level. We also design a constant time container for insert, delete, and lookup operations. GeminiFS also allows user can set the page size and the prefetch policy for page cache to tune their applications. And finally, GeminiFS provides a lib called libgemini, which contains a series of POSIX-like interface to hide complexity and reduce programming difficulty. We evaluate the GeminiFS on its I/O performance, page cache performance, and end-to-end tests. First, the I/O performance. We compared to GPU-FS and GDS. GeminiFS submits file system and a request directly from GPU, efficiently reducing I/O latency, as the right page size shows. And the left page shows that the concurrent I/O of GPU is not limited by the CPU, and GeminiFS can also maximize the bandwidth of a NVMe device at a 4K granularity, just like BAM. We also discovered the page cache performance from the prefetch strategy, parallelism, and page size. The first picture shows that prefetch can fully utilize page cache bandwidth, and the second shows with a higher warp number, page cache can deliver more than 600 gigabytes bandwidth. It would not be a bottleneck for the system. And the last picture shows if the page size is set to 256 kilobytes, the page cache bandwidth can be max. We also evaluate GeminiFS on GPU training. The left picture shows we disable offloading activation generates on training to show the benefits on checkpoint. The results show that checkpoint latency is reduced by 65% compared to the native just copy and write, and 50% compared to GDS. The right picture shows we enable the offloading activation to show the benefits for training with large batch size. And the total training time is 94% and 91% lower than the native way and the GDS respectively. Compared to remain the activation on the HBM, GeminiFS is only 4 times higher. The gap can be further narrowed by expanding the number of NVMe devices. Okay, thank you. That's all.